Hello, welcome to this video. I'm going to be talking about convolutional neural networks. Now, in a standard image, spatial relationship is everything. These pixels, those two boxes in the yellow, are neighbors, and together they tell us that that is an ear tip. Now, when we flatten this image for a normal neural network, we destroyed that spatial context. The pixels that once formed an ear are now scattered across a long list. The network has to work 1,000 times harder to realize they were even related. So a convolution is a process of feature extraction where a computer scans an image to look for specific visual shapes. It works by sliding a tiny visual pattern called a kernel across the pixels of an image chunk by chunk, where the image pixels closely match the kernel's pattern. The math produces a highly elevated score. By the time it finishes sliding, it creates a brand new grid of these scores, turning a messy photo into a clean map of extracted features, and also preserving that locality. So this is why we need a convolution. Instead of stretching the image out and losing the map, we use a kernel to scan the image in its original 2D form. It captures the local patterns, the spatial correlation, before we ever turn it into a list of numbers. So you can see that it goes box by box, right? Preserving that local structure. And finally, it goes through everything. So let me give an example with convolutional neural networks with multi-channel inputs. We saw a 2D, now we're going to see things in 3. So you can see, like, from left to right, the original cat image, right? We've got a kernel, which is that yellow cube, the input volume, right? The 6 by 6 by 3, that's the input pixels, which are the actual raw data. And the kernel's container are the weights, which you see on the far right with red layer weights, green layer weights, and blue layer weights. So it's important to keep in mind that the kernel, right, is 3 dimensions, right, by that last 3, and same with the input volume. We've got 3, so the red, green, and blue, the RGB. Now we multiply these input pixels by the red layer weights, and we could see that for the first one, we get 2295. And we put that into a feature map. So I want you to notice the 0.5 marker here. In our CNN, this represents a consistent weight, or what we call parameter sharing. While a normal neural network tries to give every single pixel its own unique weight, this system is smarter. It uses the same consistent kernel to to scan the entire image. This is why CNNs are so much more efficient at recognizing objects. So we just go on to the next section of the input volume, and it maps to 765. Next one is 0. Another 0. So that happened 4 times, right? We made the stride 4 strides. We do the same thing, right, for the following row. And finally, we should have built a 4x4 feature map with the following numbers. So 16 convolutions have happened, and that's equal to 1 forward pass. So it's important to keep in mind we aren't doing this one after another. We're running 4 different filters over the image simultaneously. It's not just looking at pixels anymore. It has one map for vertical edges, one for horizontal, and so on. It's now ready to combine these simple shapes into complex objects. Now we apply the ReLU activation function. We don't just do this to one map, we apply it to every single pixel in our entire feature volume. Like a scanner, ReLU sweeps through, instantly turning every negative signal into a 0. Activates the network, leaving us with a clean map where only the most important features remain. So you see that negative 300. And that will go to 0. You see the negative 100. And that also will go to 0. Now let's discuss max pooling. We see that in that quadrant, that upper left quadrant, that 2295 is the maximum value. In the second scenario, our cat has moved. When we look at the face patch, our ear signal 2295 has shifted over by 1 pixel in the map. But look at what happens in the max pooling layer. Because its signal is still within that 2x2 neighborhood, it still picks the 2295. By the time this data reaches the feature vector, this shift has been neutralized. This is something important called translational invariance. It ensures the network recognizes the cat's features regardless of their exact coordinates. You can see that that's 2100, the max. And then finally a 0. Now we just did that for that yellow feature map, but we have to do it 4 times. And we have to create a 1D from these. From that, we could apply a neural network. So when you unroll the pooled feature map into that flattened vertical list, you're not destroying the order. You're systematically mapping it from a 3D coordinate space, height times width times channel, into a 1D sequence. Because this unrolling process follows a strict unvarying sequence every single time, top left to bottom right, color channel by color channel, the relative positioning and organization of the extracted features are perfectly locked in. The final classification layer relies completely on this exact preserved order to know which numbers represent the ears, the eyes, or the background, for example. So we've just watched our raw pixels forward, travel forward through the entire network to make a final prediction. This completes one single forward pass. But a neural network only learns when it makes a mistake. At the very end of the line, the network calculates its final classification error. Then backpropagation takes that error and drives it all the way backward to physically rewrite the numbers inside the 4 original kernels we started with. So gradient descents tunes their weights so that the next time the network looks at an image, it sees those edges and colors with much higher accuracy. And finally, after that backpropagation and gradient descent, after gradient descent, we get the correct classification of the cat. Thanks for watching, and I hope to see you soon.